Okay, I guess we can start. So I have the pleasure today to host Colin Fox, who is an associate professor at the Department of Physics in the University of Otago. I don't know if it's pronounced correctly. Okay, in New Zealand. He's visiting Vancouver to meet his friend Bob Russell at SFU, but he also decided to present here, happily for me. So we met in Heidelberg in August at an IWR colloquium. I did my master's there, and he was presenting a talk about base optimal filtering in the tensor train format, which I found very interesting because my work is somewhat related to this. He was in collaboration there with the uncertainty quantification group. He's also a founder and editor of this Science journal for uncertainty quantification. He's working at the intersection of numerical analysis and statistics, and he has applications in sea ice analysis, and glaciers, as well as acoustics. He has worked on working on concert hall acoustics, for example. And yeah, I'm working on related methods, so I thought this would be really a good way to think about integration of Bayesian inference and numerical analysis. I hope you get something out of the talk.
So, Johnny, nice to see you all here. So today I thought I'd talk, so as Christian mentioned at Heidelberg, I talked about some work that's a little bit more advanced about how to use PDE solvers to do sequential inference or filtering. So it's kind of at the techie end of things. But all of this work that I do is what I would think of as numerical analysis of multi-chain Monte Carlo methods, or MCMC as that's abbreviated, so sampling methods or inference. So I do a bunch of work in computational Bayesian inference for large-scale problems, and I would say that the current state of technology of computation and statistics is akin to numerical analysis in about the 1950s, or perhaps 1960s, something like this. And so today I'd like to show you some kind of baby steps, some first steps in this stuff. So I wasn't quite sure what the audience would be, what your background is, what you know. Albert here has got an idea about everything. So, excuse me if I tell you things that are kind of a bit simple for you, but I thought I'd show you some work that just connects statistical inference and numerical linear algebra at kind of a base level. Just to give you a bit of a glimpse, and give you a little bit of a glimpse of the statement that I say that sampling methods are like very early numerical methods and what we should do about it. So this is work I did with a couple of people, so you know what I look like. This is Richard Norton over here, but Al Parker kind of kicked this off maybe 10 years ago. I think we decided to have a look at some of the relationships between numerical linear algebra and the methods for sampling for probability distributions. Oh yeah, so I put the title that says Polynomial Acceleration of Gibbs sampling, in case you didn't know I added a little thing about probability distributions, because I don't know if you know what Gibbs samplers are, but they're means of drawing samples for probability distributions. So some time ago, my interest is largely in non-Gaussian distributions and general distributions that come from industrial applications, so they have no special form. But Al was an expert in numerical linear algebra, and so we decided to do the Gaussian case. So largely what I'm going to talk to you today is about sampling from Gaussian distributions. So they're a little like quadratic functions for the optimization world. They're kind of a canonical thing. You know, nobody's terribly interested in optimizing quadratic functions, but if you can optimize quadratic functions, well, you can use those methods for other things. Same deal for Gaussian distributions. In fact, what I'll show you is actually the methods for quadratic functions are exactly the methods for sampling from Gaussian distributions. And so Gaussian distributions have the same role. If you can sample from them, you can use them for other things. We won't talk much about sampling from other things, but so largely today I'll just show you this work between numerical linear algebra and Gaussian distributions, because there everything is exact, and we have theorems, and there's no looseness or anything. So I'll show you that. So I thought I'd just talk about a few things, introduce the kind of problems that I work on, so you get some notion of that. Talk a little bit about optimization versus inference, because in the signal processing world, or the image processing world, which I come from, there's largely two schools of doing things, but there used to really be one school of doing things, which was that you used optimization to find the best answer. And these days we want to do inference, we want to look at all possible answers, and that seems like a ridiculously large problem, but what I'll show you is really the same thing. And so our job today is to take things from optimization and turn them into inference things. And that's a little bit of a I don't know, a meta thing that I decided a while ago. So I was talking to these guys earlier over lunch about inference methods clearly give better answers in some sense to problems in signal processing, image processing, and so forth. But traditionally they take a lot more computing, and so that's one of the reasons I would sometimes build methods for engineers, and they would give better answers, and they say, oh well, that's very nice, but I'm going to use this optimization method because it's faster. And so at some point I realised that if we're going to win the battle, we have to at least do better than optimization methods. And there's no theorem out there that says sampling methods have to be slower than optimization, they just happen to be. And so basically we started this business by stealing methods from optimization and turning them into inference. And in fact these days we have methods for doing inference that are faster than optimization. And so I won't really show you those, but I'll show you. So at some level we really want to work at a distributional level, and that's about accelerating this Metropolis Hastings MCMC. So I'll show you a little cartoon of that to give you an idea of what that's about. But then I'll talk about the business, which is today about accelerating Gibbs sampling, and I'll do some things and present some theorems and stuff and show you some examples. Now, there's quite an industry out there in the academic world building sampling algorithms. Things called Mahler and HMC and other alphabet soups. They turn out to be exactly examples of things I'll show you, though it's not often known that. And indeed, I learned that this group, I think this group has ALA of some kind, so I presume some people use the stochastic gradient method. Turns out that the stochastic gradient method is exactly a Gibbs sampler as well, and I'll show you that. Yeah, so people think of these things as different things, but really they're the same thing. So just to show you a bit of an example of what I work on. So here's a problem that I worked on some years ago. Typical kind of large-scale inverse problem. So this happens to be a field in the north of New Zealand, the North Island, a place where you dig a hole in the ground and steam comes out. And this is a power generation plant. So most of what you see is shed, and this stuff, that's silage for the cows, I think. But this bit over here is a few megawatt plant that uses the steam outlet. And so the company who was doing this were interested in increasing the production of this plant, and they wanted to know what that would do environmentally. So we've had cases in New Zealand where these geothermal power plants like this are fired up, and then some years later somebody's house collapses into a hole in the ground. Because, not surprisingly, if you release pressure out from under the ground goes downwards. Sometimes somebody's house is on top of that. And so now, to get resource consent for these things, the people who want to do the production have to make statements of what the usage will be over 50 years' time, put some bounds on how certain they are that of land subsidence and so forth. And of course, for investment, they want to know some notion of what power they can generate, what the return on investment is going to be, that kind of thing. Yep. And so what we do is essentially an inverse problem. We take surface measurements of pressure and temperature, or near surface measurements, and from that we infer the structure, the geological structure under the ground, and also the heat inputs. And from that, we then make predictive statements about what power generation will be and so for 50 years. And so all of that requires us to not just make estimates, but to actually make statements of probability. So produce distributions over all of those things. So not just work out the geology, but work out all possible geologies and what risk there is associated with the various geologies. Yeah? And you need that for investment because, you know, it's one thing to say, you know, I think if you put in $5 you get back $10, but you know, maybe you'll lose your shirt as well, and people want to know what the relative probabilities of those things. Okay. So I'm not going to talk much about that problem, just to show you kind of a picture like that, and show you what a Bayesian hierarchical model looks like, at least in kind of pictorial form. So we often draw these, what's called a directed acyclic graph for a Bayesian network. It's kind of a blobby thing with latent fields in the kind of roundy regions, measured data in the square things, and conditional relationships by the arrows. So in this case, this is how the geothermal field was modelled. So you can see that kind of thing in the middle. That's actually a temperature plume that we've predicted, and it's a block that's 20 by 20 by 6 kilometres deep, I think, is the size of it. And the thing we actually measure is near surface temperature down boreholes. So this thing on the right-hand side is actually a trace down one borehole of the temperature, and that particular borehole goes down 1,500 metres, but the depth of the region we're modelling is about 6 kilometres. So we don't really get information at the bottom. And how do we do that thing? Well, of course, we build a PDE model that knows about conservation of energy and conservation of matter and multi-phase flow and all that stuff. And it's predicated on having a model of permittivities or permeabilities. So that's the thing in the top left up there. And it's in a round region because that's something we don't know, and so we model that in a stochastic way. And in this case, we've modelled it as a Gauss-Markov random field. It has about 10,000 parameters in it. And we also don't know the boundary condition at the bottom. We don't know how the heat comes into the system. So that's this roundy blob down there, and it's modelled by, well, the geologists have been there before, so we have some idea of what's going on. So this is a 41-dimensional representation of possible heat inputs, some uncertainty. Those two things go into a big PDE model. If you know the heat inputs and you know the permeabilities, you have a classical boundary layer problem, so you can put that in your computer and like this. So that's what the dotted lines do. They say there's a deterministic model that takes you to the temperature plume and a deterministic model that takes you to the temperatures of the place you measure, and then there's some observation errors on those sigma T models. So that's kind of your forward model of probability. So if you knew each of these things, you could go forward by a PDE solver and work out the data you measure. The question is, given the data we've measured, can we put probability distributions over each of those things and make statements? And from those distributions, then predict forward to what future data. So I don't want to say too much about that, other than say there's a big simulator in there that I think Tough2, which is a code out of the environmental science world, big rusty Fortran thing. And it takes about 30 to 50 minutes on a decent-sized machine to simulate one step of this thing. So the question is, how do you go around the loop? How do you do something rather to make infinite statements of this thing? So here's a paper that's written about that, and so you can see from I wrote up the title here, so you can see that it's a adaptive delayed acceptance with Gauss-Seidel algorithm. So some fancy kind of technology for Metropolis-Hastings algorithms that allows you to do this. So I'm not going to talk about that stuff at all. I'm going to talk about something else. So in a certain sense, the early part of my work might have been how to do sample-based inference, and these days my sole interest is how to not do sample-based inference. So this is some kind of peak of technology of that world, and it's I don't know, things get complicated. So I'm going to kind of go back to the base and just talk about sampling and probability distributions and about what we do. But before that, I thought I'd just mention a couple of things, just a little bit about abstract structure about Bayesian formulation. So what is it we do? So essentially we have, so I'll use this notation throughout. So I think of you can think of that permeability and the heat input as somehow a state of nature. That's what That's what's out there in the world that we're trying to learn about. And D is some observations that we make that's related to it somehow. And often there are parameters in the system that we need to put in. So for instance, there might be features about the boreholes that we don't quite know, but we also don't really care about. And those would be things we call hyperparameters. And really what the Bayesian method does, it gives this decomposition. It says that the distribution over x and theta, all of the things that you don't know, given the data, is some constant into these distributions. The distribution over data, given the things that you know, so that's essentially the way your PDE solve and probabilistic modelling, and then these distributions that you put over the things that you don't know, the latent fields and so forth. Okay? So that's basically the thing that we do. And what's the deal? What's the issue with all of this? I mean, in a certain sense, it's a computational job, but there's kind of big issues associated with these things. And the first of all is that in all problems, our parameterization of nature is not true. So for instance, I talked about permeability under the ground, the rate at which water flows through dirt. There's no such thing as permeability. You cannot dig up a piece of dirt and measure its permeability. And any of you who are gardeners know this, because if your garden gets very dry and you want to water it, what you do, you spray the hose on and you wait for a while before the first bit soaks in, and then you can water it because it soaks in. So the permeability changes with the history of the dirt. Yeah? There is no single thing called permeability of dirt. Now, so that's part of it. So in all systems, particularly in geophysics, the variables that we need are proxies for some more complicated process. So that's the first thing I'd say, descriptions of nature. When we evaluate this term, the data given state of nature, well, of course, that requires this large physical solvey thing, a big piece of code that runs for an hour, that does all sorts of complicated physicsy stuff. Yeah, that's a pain. And indeed, the physics and the geometry are uncertain. So physicists like to claim they know things, you know. So when physicists make rules, they call them laws of physics, you see. That's to impress you to think that it's somehow correct. Well, you know, they're kind of correct. And in fact, in all inverse problems that I work in, the biggest uncertainty is in fact the physics. So people often talk about observation error as being the source of uncertainty or something like that. Actually, it's the physics is the biggest source of uncertainty. So that's an issue. You know, our models are incorrect. The other thing, of course, is that the data is sparse and uncertain. So the data itself is not everything that we wish to measure, and it has some errors in it. And so these are problems that are particular to this geophysics problem, but I work in a bunch of other areas. So I work in linguistics, determining the evolution of languages based on current observations. Phylogenetics, you know, the inference of genetic structures or evolutionary paths based on current observations. Manufacturing and so forth, and all of these share exactly the same problems. That essentially the models are wrong, and your data is not what you want. And in the presence of that, you'd like to make predictions. So other than just to give you a kind of a scary sense about that, I'm probably not going to talk much about that stuff at all. Just to say that that's kind of the place where we are. But just to talk about these two frameworks, optimization and inference. So as I say, when I started off in the business, I had my supervisor once said to me, you know, it's easy to solve every problem. You find a criteria of optimality and optimize with respect to it. So you decide what you think best is, and then you optimize. It's easy. Turns out that's a load of nonsense. So, not for obvious reasons, but it turns out that, really the statement I put in the middle that says conditional estimates gives poor predictive densities. If you're uncertain about something and you say you know what the answer is, almost certainly you will make predictive nonsense from that. And that's a provable statement in statistics, but it's kind of why optimizing is not a good idea. But be that as it may, I want to talk about computational methods associated with optimization. So optimization you can be thought of in terms of this modeling structure that we had And in some sense, usually is done in a way that, up to regularization, tries to best fit your observed data in terms of the model. So it tries to find the best model, and often in terms of interpreting the data. And so, so that's the kind of form up on the top line there. It's you minimize something that's the log of this distribution over data given your unknowns and some regularizing term. And really what I want to say was about the computational methods. So how do we do that in the computational world? Well, back in the 1950s, we would use stationary linear relaxations. So if you want to solve a linear system, for instance, if the term you were minimizing was quadratic, you form local linear approximations and you use a local solver that's stationary in the sense that you use the same iteration operator every time. It's linear because it's a linear iteration on the space of solutions, and it's what people call relaxation. So that was kind of the state of play in about the 1950s. And soon after that, people worked out some other things to do, how to accelerate such methods. So I'm going to talk a little bit about sheep polynomial acceleration. I mean, these days there's lots of other methods, the Krylov space methods like conjugate gradients, there's methods for non-symmetric forms, GMREs, there's multiple methods, fast multipolar representations and so forth. So lots of technology that's been advanced since then. One of the things I would say about the models, though, is that essentially all the models that are used in that world for optimization, well, not really. There's discrete optimization as well, but certainly all of the cases that I've written down there require continuous spaces. So essentially Euclidean kind of spaces for the representation of your unknowns. Now, as I say, the reason that you don't want to do that is it turns out that if you claim you've got a best value out of fitting data, that's not the best value for functions of the data. So in particular, best fit to data is not best fit to parameters. And I'll show you an example of that in a second. It's not a very complicated thing. So in fact, all numerical analysts know this. They know that error and residual are not even monotonically related. So making one good doesn't make the other good. But that's another issue. So what does inference do? Well, inference instead tries to evaluate expectations of some function. So if I've got some function of my unknowns, electricity production in 50 years, I want to in some sense generate the expectations of the most likely value, the uncertainty, and those kinds of things. And those are done by integrating over these distributions that you might approximate on Monte Carlo. So one way you can do that, and the way that I'll really talk about it, is you take samples from this distribution, and the weighted average of those things gives you an approximate to the Monte Carlo. And so the basic issue of inference is reduced to the job of sampling for the probability distribution. And so if you can do that, you can evaluate expectations and you can solve the problem. And how do they work? Well, the fancy methods these days are the Markov-Chain Monte Carlo methods. An example of that is this Gibbs sample that I'll talk about. There are actually fancier methods out there. So there's IMLA, which is a nested plus approximation. There's this randomized and optimized, which is a much better method. There's methods based on tensor train approximations that were mentioned to Christian. I'm not going to talk about any of those. Those are kind of flash methods with chrome stripes on them. I'm going to talk about the one that 99.9999% of people use, which is this Markov-Chain Monte Carlo, particular Gibbs sample. Now, one of the things that's good about these methods is that they can work on more general spaces. So in statistics, it's common to make models that live on arbitrary measure spaces, and the algorithms can work with those. And those spaces can be continuous or discrete or whatever you like, some mixture of those. So for instance, I mean, a common example I give people is say, let's count the number of tables in this room. So counting tables, well, that's a thing that you cannot do with Hilbert spaces. So if you're in the optimization world, there is no way of counting. All spaces are linear, there's nothing about discrete spaces, there's nothing about 1 and 5, that kind of thing. We can easily build a discrete measure space that has 1 table, 2 tables, 3 tables, and so forth. That's not a linear space, but we can easily compute with such things in the Markov-Chain Monte Carlo world. So these have advantages that they can work with much more general spaces that are descriptive about the problems we're trying to solve. And so in a certain sense, our job, task for today, we gave ourselves, is to kind of mix and match the best of these worlds. Can we make methods that work in these general spaces, but that steal the flash methods from optimization? So we steal the acceleration and so forth. So that's what I'll show you today, is how to do that. Yep, so we want to not be apologetic about using inference methods because we don't have these flash numerical methods. We want to steal the numerical methods and be able to do the job we want. And in a certain sense, optimization and sampling really have the same job, that you get given a complex function of a high-dimensional space, and you're trying to move around the thing using local information. Yeah, so optimization algorithms try and move around using local information to kind of get up to the top of the hill. Inference algorithms try and move around to go everywhere. And you spend more time where there's bigger probability and less time when there's less. But that's what you do. Again, you're using local information to kind of move around. And so a lot of the ideas that come out of optimization, you should be able to steal and put into sampling algorithms. So that's what we'll do. Yep, and I just thought I'd show you this little thing about stochastic bias, because if you don't believe me that conditioning on estimates gives you bad predictive densities, I've got a little lemma here, which is about the simplest lemma in the universe. It says that you've got some random variable, so some variable with a distribution, and it has mean value mu and variance z, variance sigma squared, so that's some kind of spread of the distribution. And the expected value of z squared is mu squared plus sigma squared, and there's a little proof. Yeah, it's really nothing. But it does mean that if you have a nonlinear function of a random variable, then the function of the best value is not the best value of the function. And those two things don't commute. And so here's a little simple example. I teach electronics, so I teach this to my students. I say, so here's some graph of voltage. So I drew by hand. So you can decide whether it's random or deterministic. It really doesn't matter. That's not the issue. Yeah? And it kind of goes up and down. And they're going to say to you, this is some voltage plus or minus some other stuff. What's the best estimate of the voltage? Yeah? And you say, oh, I'm going to find least squares, because that's how you do best. And so you find the best voltage by finding the thing that minimizes the sum of squares to some constant. Yeah? And if I've drawn my picture well, the constant is 0. Yeah? You're best interpreting that picture by saying 0 plus or minus some stuff. Yeah? But if I then ask you the best power of that graph, you wouldn't say 0 squared. Because the power, of course, is the square of the voltage, and that's entirely positive. And so the average value of the positive thing is going to be something positive. Yeah, it's not going to be 0. Yeah? So here's a simple case where the best voltage is 0, but the best square of the voltage is not 0 squared. Ta-da! Ta-da! It's not really like, so complicated, is it? It's completely obvious. Okay, so how do you fix this? Well, what you do is you don't say, in the presence of uncertainty, you don't say my estimate of the voltage is 0. You give me a histogram of all possible voltages. So if you plot a histogram of voltages and you say, well, that's some kind of bumpy thing, and maybe the most likely value is 0, and then you want to answer the question about the square of the voltage, you square that distribution, and you get a correct distribution over the square of the value. And then you can point to the peak of that, and you say, that's the best estimate of the square. So the truth is, in the presence of uncertainties or variability, because I don't know if I drew that graph as random, which doesn't matter. Yeah? What you have to do is you have to track distributions on things. So you don't give a value. If you've got uncertainty and you say the answer is 0, and then they say, oh, what's the best power? You'll make a terrible prediction. What you've got to do is keep the distribution over values. And that's exactly what sampling methods do. They essentially track distributions and allow you to make statements of best of each place you use. Yep. So statisticians say this conditioning on estimates gives you poor predictions. That's their kind of technical term for this. But you know, as you can see, it's relatively straightforward. So that's really the reason that you need to track uncertainties, track distributions. Okay. And obvious to everybody? Not the world's most complicated example, is it? No, good. Okay, so let me tell you about XMC in a nutshell. So Markov chain Monte Carlo methods. So the vast majority of them, as I mentioned, The job that we're going to do is explore distributions by drawing samples from them. And why do we do that? So we can evaluate expectations of arbitrary functions f by this Monte Carlo estimate. You might say, why not use a weighted Monte Carlo estimate? Okay, we can discuss that some other time. But here's the kind of plain vanilla version. And what's a way of generating samples from a given distribution? Well, here's a very simple rule worked out by somebody when they're in hospital playing cards. And it's this. So you make a proposal. So what we're going to do is we're going to build a Markov chain. That is to say a sequence of random variables. And I'm going to build it by this stochastic rule. So my stochastic rule is, when I'm currently at state X, I make some proposal to go somewhere. Yeah? Use some random rule to propose a new value. And then I accept or reject it with this ratio here, something metropolis has to for. And this thing, so I go, should I go there? And you go yes or no, probably this rule. If you say no, you go back. If you say yes, you stay there. And off you go. Yeah? This is guaranteed to converge in distribution to the target density pi. Yeah, I'm not going to show you how to do that. It's not very hard, but that's what it does. What the thing I really care about to tell you is that this thing is a stationary linear iteration on the space probability distribution. So this simulates a transition kernel. So this doesn't evaluate a transition kernel, because if you think about probability distributions, so probability distributions is the distribution over all possible solutions of your problem. So the solution of your problem might be a big vector, 10,000 things, but the space of all possible solutions is even bigger. Yeah? So this is a function of all possible solutions, and so there's no way that you form that transition kernel, but you can simulate it, and that's what this thing does. It simulates that transition kernel. But in terms of the probability distributions, if I ask you what's the probability distribution over the n plus 1 step, it's the probability distribution of the n step multiplied by this kernel that we can work out. Yeah, so it's a linear iteration on the space of probability distributions. And it's stationary because it does the same thing every time. Yeah, so every time you draw the same cube, compute the same rule. Draw the same cube, compute the same rule. Yeah, so you are simulating a stationary, a fixed transition kernel, and it has the property that asymptotically it converges to the right density. But it does the same thing every time. So what you do is you get this, your probability distribution, you start off with some probability that you first draw the sample, and you go bang, 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 bang. Yeah? And it converges to the right thing. Now, so I say this because those linear iterations that people used to do optimization in the 1950s were exactly this. They were stationary linear iterations on the space of solution vectors. Yeah? Now, solution vectors might be, a vector of 100 or 1,000. Well, I don't know, you're designing an airflow around an aerofoil. It's millions or something. Yeah? People soon worked out that if you used stationary linear iterations, you would die before you got the answer. The universe would melt before you get the answer. And yet here we are working on much bigger spaces, and we're using exactly the same technology. Yeah? So, not surprisingly, these methods are slow. They're so slow that you go to cabarets by computational statisticians who sing songs about how slow they are. That's how slow they are. And it's precisely because they're a stationary linear iteration. So that's the thing we're interested in. Yep. So that's standard. This is the pinnacle of technology in the vast majority of computational statistics. So what they do is they worry about this proposal density and a few other bits of nonsense, so that they get the best possible P, but it's still the same P every time. So that's a basic issue. So let me just show you a little cartoon of accelerating MCMC. So what I said was that, and notice that I put vectors on the left-hand side. So I put matrices on the right-hand side. That's how statisticians do it. You might have grown up in a world in which you drive on the other side of the road. Statisticians. Yeah? So I say pi p, so that's the vector pi multiplied by the transition kernel p. Yeah, and what I've said is the n-step distribution, then is the zero-step distribution by p to the n. For some odd reason in numerical analysis, we calculate this error distribution this way. So if you want to ask me what's the difference between the n-step distribution and the one I care about, we go like pi naught times pi minus pi, the initial error, by p to the n. Yeah? So I just raise that kernel to the nth power. And we numerical analysts, I should blame our lid for this because I'm not really numerical analyst, like to write error polynomials as a function of I minus p. But the critical thing, if you write in terms of the eigenvalues, it looks like 1 minus 1 to the n. That's just raising the fixed polynomial to the nth power. So that means convergence is geometric. So statisticians get very excited about what kind of geometric convergence they have. I think geometric convergence is terrible, and so they should ignore all those fine details. Okay, so what does polynomial acceleration do? It says, can we modify the iteration in some way so that the error polynomial, this thing up here, 1 minus lambda to the n, is better in some sense? Yeah, can we muck around with the iteration so that polynomial is smaller? And let me just show you a kind of a cheap version of that for general MCFC. So what I'm going to do is I'm going to consider subsampling with weights. Yeah, so I'm going to run my Markov chain for a while, generate a few states, and then instead of taking the last one to move on, I'm going to subsample one of these. I'm going to pick one of them at random. And so that's the one I'll use to go on with. Okay? So what does that do? If I have xi and I choose with probability alpha I, then I get this mixed distribution like this. See? Because one step I get p to the 1, 2 steps I get p to the 2, 3 steps I get p to the 3. So if I choose one of those at random, I get a mixture of that polynomial. I get some mixture of p to the 1, p to the 2, p to the 3. And so my error polynomial is now a sum of these things. Yeah? And so because I can choose the alphas, I can choose the error polynomial to some degree. The alphas have to be positive, so I don't have a complete free range. I don't have a subsample of negative probabilities. Yeah? And so we can choose the alphas, so we can choose the error polynomial. And so here's a simple example, the simplest example I can think of. Yeah? So let's say we want to sample from the probability mass function of third. So I have 3 states, and I want to do them with probability of third. Not very complicated, I know, but what's wrong with that? Yep. So here's a matrix P that has the property that if I raise that, if I keep applying P, it will converge in distribution to third. And so here it is. Here's P squared, P cubed, and if I run it to P affinity, it's third. So it says no matter where I start, I'll end up with state, if I do an infinite number of iterations, probably third. Yeah, like that? Okay, now I'm going to accelerate this in the following way, by that subsampling. So I'm going to start with x naught, take 3 steps. So I get P, I get x1, x2, x3, and I'm going to subsample those with these weights. 1 upon 11, 14 upon 33, 16 upon 33. Like those weights. Yeah. And if I do that, if I subsample with those weights, ding, the thing I get is precisely a sample from the correct distribution. Yeah. So if I ran the geometric sampler, I get closer and closer, as you can see, as I'm running iterations. Yeah? But if I really want a true sample from the density, I have to do an infinite number of iterations. That's a lot of work. Or I can do 3 iterations, subsample, ding, it's exactly a sample from the density. And how do I know that? Because 1 upon 11p plus 14 upon 33p squared, 16 upon 33 is exactly p infinity. Ta-da! So there's an example of polynomial acceleration. Yeah? I've mucked around with the iteration operator so that I can play with the error polynomial. In particular, I can choose the weights so that I get the error polynomial that's best for me, in particular 0 each of the eigenvalues. Ding! Works perfectly. Less work, better answer. That's what we want. Yep. Now this is a bit of a cartoon, as I say, because there's restrictions on this. I have these positive coefficients. You're also going to say, well, thank you for telling me how to sample on a space of 3 things. You could probably do that some other way quite well. Interestingly, we can play exactly this trick for Gaussian distributions. So that's a case where we're on a continuous space. So we have an infinite number of states. So even a univariate random Gaussian distribution, you take any value on the real line, lots of values. Yeah? And it turns out Gaussian distributions, we can play exactly this trick and make what you call a perfect sample. So we can make a finite number of iterations converge exactly. And so I'll show you that. So here's a multivariate normal distribution. So I should speak up, shouldn't I? So here's a multivariate normal distribution defined by a precision matrix A and a mean mu. And I'm particularly thinking of the case where the matrix A, the precision matrix, is larger than sparse. So that's the typical case. So there's a typical Gaussian distribution. And think of these two jobs of sampling from that distribution, so that's the green dots, a bunch of samples drawn from the Gaussian, or maximizing, which is the red dot. Okay? And so what are those? Those are optimization. So that's argmax of blah, blah, blah. And if you take the gradient of the logarithm of this thing and maximize it, that's a gradient of the quadratic, so that's a linear function. Yeah, so that's exactly the job solving AX equals B. Yeah, so that's how you do that. And sampling is this job, draw samples from pi. What I'm going to show you is that solving AX equals B is exactly the same as sampling. Really, it's the same working problem. So, there's a bunch of methods out there. So if I told you that sampling and solving were the same thing, and you had a small system, you would be tempted to solve your system using a collective factor or some factorization, pure factorization, something like this. And indeed, these are an example of a more general notion of mutually conjugate factorizations. So if you can find a set of vectors that are mutually conjugate with respect to A, then they essentially diagonalize your matrix, and they allow you to sample on the diagonal and generate a sample from that distribution in any step. So there's various ways to do that. If you've done statistics, you probably know about Eigen decompositions of A give you independent directions of a Gaussian. In fact, the more general statement is mutually conjugate. So any of these methods will work. So these are kind of direct methods based on factorization. They work well up to a certain size of the problem, but let's say A is 10 to the 12 by 10 to the 12. Perhaps some factorizations are expensive, so we do other things. So the basic method is, that we're going to talk about, is Gibbs sampling. And Gibbs sampling, in its basic form, is a coordinate-wise sweep of conditional distribution. So here's a sweep of component-wise Gibbs sampling. It says, what you do is you pick the first direction, you take a slice of the distribution, for Gaussian distribution, it's Gaussian, you take a conditional sample. And then you take the second direction, sample in that direction, take the third direction, and off you go. So that's a Gibbs sample. And there's lots of things you might ask about that. I mean, one of the things that got me into this business is, in statistics, in the early papers, this was referred to as stochastic relaxation. In numerical methods, we have a notion of relaxation as kind of a technical term. And I was kind of curious whether those two things were related. It turns out they're identical. That's what I'll show you. So to kind of, I don't know, not show you lots of math, but show you some pictures. So here's a kind of a pictorial version of the end of this analysis. So at the top there, I've drawn a picture of the contours of a quadratic function and classical methods for optimizing them. At the bottom, I've shown the contours of the associated Gaussian distribution, so e to the minus quadratic. I've shown you the contours. And up the top, you see, is the first one is Gauss-Seidel optimization, and down here is the Gibbs sampling one I just showed you. Yeah, so this one does these conditional samples in each direction. Now, if you look at Gauss-Seidel, I don't know where Albert says this in his course, but then you can see it does these coordinate-wise optimizations. And you can see that the step size gets smaller and smaller as it reaches the optimum. So that's a kind of telltale sign that the convergence is geometric. And what we'll see is that it's exactly the same iteration as the Gibbs sampler. So that means Gibbs sampler is geometric. And so once you learn Gauss-Seidel, what you do, you flick over a few more pages in your book on numerical methods and you learn about Chebyshev accelerated Gauss-Seidel. And so here's a Chebyshev accelerated optimizer. And you'll see that it walks into the minimum much more quickly. The step size still decreases, so it's still geometric, but it's a lot more efficient. And here is the equivalent sampler here. So here's the Chebyshev accelerated Gibbs sampler, and it has exactly the same rate as the Chebyshev accelerated Gauss-Seidel, which is optimal in some sense, and so this is optimal in some sense. If you allow your iteration operators to depend on the residual, you can build better methods like CG or Lanchos. And it finds the optimum in 2 steps, the number of distinct eigenvalues of your matrix. And And likewise, you can build a range of sampler, and every 2 steps gives you an independent sample from the distribution. Okay, 2 steps, ding, 2 steps, ding. And you know, what your teacher in numerical analysis should tell you is that the cost per iteration of each of these things is essentially identical. So running this is no more expensive than running this or this. And as I say, this is the current state of art in statistics, something as in statistics. You know, and nobody would run Gauss-Seidel on anything reasonable in the numerical world, and so it gives you some idea what you do. Yeah, so basically the program is we want to build these samples and so let me just quickly show you about the kind of technical details. So how do people introduce linear iterations for solving systems of equations? Well, typically it's done by this matrix splitting form. So if you want to solve Ax equals b, then I split the matrix into m minus n, and m is the thing I'm thinking that easy to invert and will approximate the inverse value. And so you can rewrite Ax equals b in the second form, and it gives you this iteration here. Yeah, so that's the standard iteration that people use for fixed matrix splitting for solving linear systems. And a common one, for instance, is Gauss-Seidel, and it uses the lower diagonal and upper triangle parts, yeah, and it gives you this iteration here explicitly. And so you can write Gibbs sampling for Gaussian distributions in exactly the same form. So I've written one sweep of all components of the Gibbs sampler, kind of just to chase. So here's Gauss-Seidel. Yeah? And you see that they're essentially identical in terms of the iteration operators except for the last term. So whereas Gauss-Seidel goes linear iteration on x plus a constant, linear iteration plus a constant, Gibbs sampling goes linear iteration plus a random thing, linear iteration plus a random thing. Yeah? So both of them do the same job. They both implement this what I would call first order regressive iteration. They take y as equal to some matrix on y plus a vector. For sampling, the vector is a random thing. For Gauss-Seidel, it's a fixed thing. Okay. But the iteration operator, the matrix G, all this nonsense here, is exactly the same. Yeah, and this was known in the 80s and 90s. It's not new. But here's the theorem that the Gibbs sample converges if and only if the solver converges. So if you build a matrix splitting method for which it generates a convergent linear solver, it generates a convergent Gibbs sample. Exactly the same thing. And really it boils down to both converge if the spectral radius of G is less than 1. So that is to say that convergent splittings, or if you put them in this first order form, what are regressive operators, generate generalizations of the Gibbs sample. Yeah, so they're really the same thing. Same rates of convergence, same conditions for convergence. One converges in distribution, the other one converges in value, but you know, that's the thing. So you can design the noise term, the random term explicitly. So you want the variance of the noise term to be n product plus n. That guarantees that you converge to the right Gaussian distribution. And here's a little theorem that just says you converge with this iteration. So both are really exactly the same thing. Okay, so that allows you to go off to your numerical analysis text, find a bunch of matrix splittings that are your favourites. Each of them generates a Gibbs sampler. And in fact, the rates of convergence and the proofs of convergence are exactly the same that come out of numerical analysis. Yeah, so here's a bunch of facts which to a numerical analyst on the right-hand side are standard statements about the regimes of convergence of Richardson, Jacobi, and so forth. These are unknown in statistics, and yet they're completely kind of ordinary in the numerical analysis world. Yep. So I've included here omega, which is a relaxation parameter. We're never really going to use that terribly much. What we are going to use is this forward and backward sweep of Gauss-Seidel, the so-called SSOR, which was discovered in statistics and it's called the regs algorithm for some reason. And we're going to use this forward and backward sweep of SSOR because it gives symmetric splitting, and so we can accelerate it using polynomials. So that's where we get the Chebyshev acceleration from. So that gets us to this point where we can accelerate the forwards and backwards sweep of Gibbs. So each 2 steps you go 1, 2, 2, 1, like that. Yeah, that's a symmetric splitting. It's positive eigenvalues, we can accelerate it. It gives us this algorithm here. Yeah. And so just to show you how that works, how does it work? When we use a fixed iteration operator, so Gibbs sampling, we end up with exactly this error polynomial that looks like something to the nth power, because we're doing the same thing every time. Yeah, so if you do it once, you raise it to the 1, you do it twice, you raise it to the 2, and so on. And how is that fixed in Chebyshev acceleration? Well, they do it by changing the splitting. So this was a trick due to Ken Goller and Richard Varga years ago. They changed the splitting to this thing that's up the top, and in particular that changes the error polynomial for each iteration. And by taking the sequence of these tors, this relative splitting, we can control the error polynomial like this. So by taking the sequence of these tors, you can generate yourself an error polynomial, and you can build yourself the error polynomial that has the best value of best error polynomial. Yeah, particularly you can choose the zeros. Now the point about this is it generates a non-stationary change. We're going to take a sequence of these tors, so every time we do an iteration it's going to be different. Yeah? So in particular, most of them will be suboptimal. Yeah, there'll be a best iteration if you've used one iteration over and over, but in general there are a bunch of suboptimal iterations, but together they make a much better thing than the best iteration. Yeah, and this has been known in the numerical analysis for donkeys. So what is the best polynomial? Well, if you want to minimize the maximum in some sense, then it's the Chebyshev polynomial. So you choose the values of tor given by this series of Chebyshev polynomial, and that gives you, so what I've done here is I'm taking a little example that's a 10 by 10 matrix, so a 10 variable problem, kind of tiny. Evaluated the eigenvalues, because we need to know the largest and small eigenvalues to evaluate these values of tor. Yeah. Fired up the Chebyshev polynomial instead of the one given by the fixed iteration. So the fixed iteration is the one in red, that shows the error, and the error is biggest at the extremes. And what the Chebyshev polynomial does is it kind of pushes it down so you get a little bit of nonsense everywhere, but it's the smallest, biggest nonsense. So in this case, even after 10 iterations on a problem of size 10, we get a factor of 300 improvement for the same cost, just by doing a little stuff. Yeah, so that's what you do. It turns out you need to use a second order method. The first order method that I showed you there is numerically unstable. Clever people, but not me, worked out how to build second order iterations, so that's this thing up the top there. I don't really want to show you very much other than to say that here's an algorithm. So you can really write an algorithm, which I don't expect you to read, but to say there exists an algorithm you can run that exactly achieves this optimal convergence rate for sampling. And here's a little computer example, tiny problem, 10 by 10 lattice, sparse precision matrix, so D is 100 size problem. Up the top there, the blue lines up the top are Gibbs sampling, so they're doing distributional convergence at some very gradual rate. And if you wait for long enough, they converge to something. Here's Chebyshev acceleration with and without relaxation parameters, and you see they scream in just fine. The green line here is Gauss-Seidel factoring, so for small problems, Gauss-Seidel factoring is fastest. Yeah, so the cost and the accuracy is given by these. If you make a bigger problem though, of course, Gauss-Seidel factoring scales poorly. And so let me show you an example that's out of a real biofilm imaging problem that we ran. So this is a 100 by 100 by 100 example, sampling and distribution. And so the Chebyshev acceleration works fine. Here's a plot of a surface of a reconstruction from this scanning laser microscope data. Yeah. And if you work out how long it would take Gauss-Seidel, it would take about 10 to the 8 times more compute time to do it. So once you get to decent sized problems, you really want these overall methods. Now, that's kind of the end of what I wanted to show you about accelerated Gibbs sampling. But I just wanted to, I don't know, put a bit of fly in the ointment about a few other things. I mentioned that out there in the sampling world, there are whole communities of people generating sampling algorithms with fancy names. And they all turn out to be examples exactly of matrix splitting. So they often have an intuition, which is very different to Gibbs sampling. So they say they have all sorts of properties, but they're mathematically identical, and so, well, what can you say? You know, the mathematics doesn't care what your intuition is. But so here's one of them, Mahler, so-called metropolis adjusted Langevin. So if you take a Langevin diffusion, this is the thing that some people in the world love, which is this differential equation at the top, that thing in the continuous form, if you evolve that in continuous time, it converges to the distribution that you wish. So people run this by discretizing it. So here's the discretization using some parameters, the precondition of V, and some step size, essentially 0, 1, and you'll see that it looks like this thing over on kind of purpley. And if you look closely enough, you will see that that's an AR1 process. So it's y equals blah-de-blah-de matrix blah-de-blah into x plus blah-de-blah-de-blah-de, which is the constant in the random term. And so it's exactly one of those matrix split signs. So we could have generated this thing by starting off with a matrix statement of density that we want, the precision matrix, doing the matrix splitting. And here is exactly, so they've got it by discretizing the differential equation, but it is precisely one of these AR1 proposals. So it's precisely a matrix splitting method as we follow. Now this, of course, people apply this over and over as a stationary iteration. This is exactly one of the things we can accelerate using these methods. Don't do that, but that's another issue. And just to say that there's a whole world out there doing these things, I wrote a table of choices of preconditioner and of theta, and here's papers and names of the various algorithms, but they're all variants of exactly the same thing. They're just choices of various things. So preconditioner Crank-Nicholson, for instance, is one of these algorithms. Stochastic Newton is another one. They're exactly these matrix splitting methods. Hamiltonian Monte Carlo, so Kristen mentioned STAN. It's the engine in STAN. Hamiltonian Monte Carlo is based on simulating Hamiltonian dynamics. So you say my current state X is a position, I generate a random momentum, and I give it a kick with that momentum and follow some Hamiltonian dynamics, and I use that as a proposal, which I accept projectors and metropolis Hastings. And if we fire up the standard leapfrog method, or as people sometimes say, well, again, I can write that exactly as an AR1 proposal. So it's another example of one of these matrix splitting methods. So they're exactly equivalent to Gibbs sampler. People don't like to say Gibbs sampler because Gibbs sampler takes these conditional samples and you think that's a pretty dumb idea. This is exactly the same in some coordinate system. So HNC is another example of one of these matrix splitting methods. Again, they run as a stationary method, should be accelerated, that's another issue. And just to poke you in the eye a little bit, stochastic gradient descent is exactly one of these. So I've only talked about sequential sampling methods where, so fixed scan methods. You go coordinate 1, coordinate 2, coordinate 3, and then we chose methods that did a fixed scan in other directions, the Chebyshev accelerator, but it's a deterministic method. I could have also started telling you about random scan methods, where instead of going 1, 2, 3, we choose the direction at random. We choose one of the coordinates at random. Now there's a theory that's a little bit more general for convergence, the so-called random iterated operators. So there's a paper by Dana Coombs and Friedman, same review in '99, that I think is very readable and very nice. But essentially, it looks exactly the same. So what I've done here is I've just taken the simplest possible problem, fitting a straight line to some data using least squares, fired up stochastic gradient, because I can get that out of Wikipedia. And so here I've written the stochastic gradient iteration as exactly one of these AR1 iterations. So you see it's some matrix into the coefficients plus some fixed vector, so it's GI plus GI. Instead of choosing the little GI at random, we're actually choosing both of these things at random. So we pick I at random, it's one of the iteration operators. So it's slightly more general than matrix splitting. But again, there's a theorem that says these converge in distribution if the big GIs, not that they have spectral radius less than 1, but that they have spectral radius less than 1 on average. So what's called contracting on average. But if they do, and it converges, that's guaranteed to converge in distribution. So the stochastic gradient method is exactly a random scan Gibbs sampling. So if we were minimizing the quadratic form using stochastic gradient, it would exactly be a sample from a normal distribution. So when people say they're an optimization algorithm, people like me say, actually they're a sampling algorithm. So it's actually a stationary Gibbs sample. Again, you can accelerate it. You can make it faster with the same equilibrium distribution by acceleration. Okay, well I think that's really all I should say. We're running out of time. More than I need to say. Maybe the only thing I really want to say is this thing that if you want to sample Gaussian distributions, then sampling Gaussian distributions is exactly solving linear equations. And indeed the rates of convergence are the same, so fast solvers are fast samplers. Okay, so that's the first thing to say. The non-Gaussian distributions, I mentioned this, so I didn't really say it, but in the same way that quadratic functions are somehow a basis for optimizing non-quadratic functions, Gaussian distributions are a basis for sampling non-Gaussian distributions. Same. You might think of a quasi-Newton method or trust region method or whatever is your favorite. And in particular, the basic iteration, which is the minimizing the quadratic form or sampling the Gaussian, whichever way you like to think of it, HMC, Mahler, stochastic gradient are exactly those things, exactly the step we have in a quasi-Newton method. There's issues about non-Gaussian distributions. We can accelerate convergence to Gaussian. Does that accelerate a general case? Maybe it does, maybe it doesn't. But really, the only thing I wanted to, other than that, which was so about this was that probably the biggest trouble with this field is that not enough people do statistics and numerical analysis and applied math. So in my university, if a person does statistics, they will never do any computational methods. So they have no clue about Gibbs acceleration. And likewise, people who do numerical methods sort of have very little idea about statistics. And so maybe the really thing I'm going to tell you is that I think that teaching students that we want to solve problems of the modern era, staff of the university need to step up and get students doing it for them. Thank you.
Do you have questions?
So, thanks for the talk. So I would argue that the state of the art for sampling from a normal distribution would not be Gibbs, but maybe more like perturber and not or similar.
Well, yeah, no, I agree with you. I agree with you. But what I would say is that accelerated Gibbs within that business of sampling is optimal. So whatever method you tell me, if you're going to run an iterative method with residuals, with iteration operators that don't depend on residual, then Gibbs is optimal. You can remove that. There is a theory. So in fact, accelerated Gibbs is the best you can do in a certain class. And then if you're going to allow yourself to have iteration operators depend on residuals, I'll say the CG algorithm. That's the best you can do.
But I guess perturber and not will also give you samples.
It must take more time.
Well, it doesn't do the same favor, so it creates a randomizer fixer, which is then maximized. And so in the maximization step, then it's free to use.
Yeah, so one of the problems with mathematics is that it can bite you on the bum. And there's a theorem that says that the rate of distributional convergence for Chebyshev acceleration is optimal. There is no better. So strangely, I agree, Gibbs of itself is not a very good method. But Chebyshev accelerated Gibbs is optimal. You cannot run an equilibrium method with iteration operator that doesn't depend on the residual. That's faster. Yeah, so numerical analysts have done a good job over the years solving linear systems. That's all I can say. Yeah, no, I agree with you. But, you know, CG, people often think of CG as a preconditioned Richardson, so an accelerated Richardson. Now, Richardson doesn't even converge, but that doesn't even accelerate convergence. So, yeah.
If these have existed for so long and they've done such a good job, then why weren't these picked up by the machine learning community first? Like, what are the barriers to entry for these methods? And why aren't they being used more? Or are you solely sort of attributing that to teaching and closed-mindedness?
I think you've already answered your own question, you know. So I don't know. I mean, so I observe that applied maths and computational maths applied mathematicians often use good computational methods because they have conferences in common. I think this is the reason. They talk to each other. But, you know, statisticians and computational mathematicians often live in the same building, but there's a rate of movement of information through the community that seems to depend on who talks to whom. So I think it's something like that. But yeah, I mean, the world's not, you know, this wouldn't be the first time that something had been invented in the field and not observed in another. I mean, maybe the goal is to try and not reinvent it in machine learning, but to steal it. But yeah, I mean, so as I say, the original version of observing that Gibbs and Gauss-Seidel were equivalent was back in the 90s. Now, why has it taken so long? I'll put that one on you. Yeah, so the short answer is I don't know, but one of the things I do think is a problem is that, I don't know how it fits about this, but back in the days of you know, when Southgate was inventing relaxation methods for solving linear problems, you know, in the 1940s and 50s, they had all these intuitions. You know, if I add 7 first and then I divide by 3, it'll be a better answer. And then somebody worked out that really all you care about is the spectral radius of your iteration operator. Everything else is bullshit. And something's still in that way. You still get people talking about algorithms. Oh, if I do this, it'll go around that way. If I do this, you know, show me the spectral radius. Everything else is bullshit. And I think the same thing's true of machine learning. You know, it's like, thank you for telling me all this intuition about your algorithm. Show me your spectral radius. Everything else is bullshit. People like discussing the intuition.
Okay, if there are no more questions, then I will thank Colin once more.